again. Here we have our lecture that goes along with Chapter 2 from the textbook. So environmental science, of course it's going to involve the environment and it's going to involve science. So we're going to talk a little bit about the basics of science and also the building blocks for everything, and that's matter, and how some of these things are connected to each other. So let's get started on Chapter 2 here. Well, first thing, what is science anyway? Because we have some kind of broad ideas about this. But what science is where you're collecting information and you're trying to make some kind of conclusions from the information that you have. And of course, the more information that you have, the more connections that you can make, and maybe the deeper the conclusion is going to be, or the more correct the conclusion would be. So that's the idea of science. We're going to keep collecting information. It's not just what I think is going on. Can I kind of show what's going on here? Definitely evolving. So there's, you can't say that the science is the answer and that's the end of it. You could say this is the best of our knowledge at the time, and then we go from there. And sometimes things that we thought were going on, we totally change our viewpoint on them, and that's the paradigm shift. So, we used to think the earth was flat, and that was the prevailing wisdom. And we don't think that anymore. So that's a little bit of a paradigm shift. And there's so many of them out there. And we're evolving as we go, but you're part of it now. Okay, so the environmental science in itself, there's a lot of things that are going to get in the way of getting a definite conclusion to what's going on. And one of them is there are so many variables. I mean, you're out in the real world right now, and we're talking about science as being a controlled experiment. You can't control everything that you're going to find out in the outside world all of the time, and that is a limitation in itself. The other thing is how long we've been collecting the information for. How far back does the information go? How much do we know? So we have some limitations right now, of course, and we're looking to build on those, or to improve the limitations, cut down on some of the limitations. All right, well, let's talk about it anyway. Everything out there is made up of matter, so that's a good place to start here. Solids, liquids, and gases, anything that has mass and occupies space. So that's everything that we're talking about, right? But once we find out about it, then we can find out how the matter is put together, and how that's going to affect some of the things that happen in the environment, and some of the things that we do in the environment and we do within industrial processes. So the understanding of this stuff has been a big jump forward, and a relatively recent one for human beings as well. Okay, so we can talk about the elements. You know that from your chemistry classes here. And the elements you can't break down. You have carbon, it's still going to be carbon no matter what you do to it. And compounds are when you start bringing in some different elements together and how they combine. And of course this is chemistry, and fascinating stuff, and a real big jump up, as I said, in human development. All right, so for environmental science, there is a lot of these things in it. That's part of the challenges here, and chemistry has a part as well. So these are the elements that you're going to be expected to know for environmental science. There's more of them, but these are the big ones. So very good for you early on to start saying to yourself, hey, let me get the names and the symbols down here, and then I can start talking about their impacts. Okay, so atoms, ions, and molecules, that's how everything is put together, so we should understand that a little bit. So we know about the elements here, and molecules are made up of two or more of these things. And then we start talking about the formulas, so we can first start talking about ions. Ions are things that have a charge to them. So here are important ions for environmental science. Nitrates and sulfates, definitely phosphates, all of these in here are going to be ones you're going to want to be very familiar with, the positive and the negative. Okay, and let's see. Okay, and then some of these things are going to form together for compounds, and these are some of the compounds that you should be very familiar with as well. So get familiar with them. I don't need to go over them. They're in your textbook, and they're also right here in front of you. Okay, so spend some time on those if you can. Try to be familiarized with them. And like everything, there's so much information to take in. So the more times you can cycle through the information, the better off you're going to be too. Sort of our own version of nutrient cycling. But the more you keep putting the information in, the more likely you are to understand all the different connections. It's a lot, but the earlier you start on that, the better. So by watching this video, you're off to a good start anyway, I'm sure. Okay, so solids, liquids, and gases. I think we're very familiar with those. And now let's talk about this idea of high quality matter and low quality matter. Matter comes in a lot of different forms. It can go from one form to another, right? And some are more useful to us than others. So we talk about high quality, like a solid, maybe the coal that we burned, to get some energy, or even the liquid of oil that we have. That's high quality. Once it becomes a gas and goes out into the air, the matter is changed to a different form, but not quite as useful to us. And yeah, actually here is the coal as an example as well, and there's the gasoline. All right, so there you go. We know that matter can change from one form to another, and it's these combinations that go on, represented in equations sometimes, when it's a change, a physical change, or a chemical change rather, that have a lot to do with how we're affecting the environment. Okay, so the physical change is, we just take it from one form to another. We have a tree and then we turn it into a table, something like that would be a physical change. We rip a piece of paper, but a chemical change is what I was talking about there with the different equations going on. And we also have nuclear things going on, and they're tied into our class as well in a couple of different ways. So let's talk about the nuclear. One of the things that can happen with nuclear is a decay. And what we talk about here is something that is decaying into different things here, and that has consequences out in the environment too. Some things are dangerous. We want them to break down, the radioactive decay. And with radioactive decay, we talk about something called a half-life. And a half-life is simply that, how much time it takes for half of what is there to decay. Sometimes that's a good thing. Sometimes we don't like it as much. Fission is going to be also a nuclear change, and that's the splitting of the atom. So we take an atom, we combine it, and we get this chain reaction where we're splitting the atom. And every time that chain goes, a lot of energy is released, a whole bunch of energy. And that was an Einstein discovery, that matter really is energy. And if we can split it, we'll release a lot of the energy. And things like uranium can be split a lot easier than some of these other things that we have. So uranium is used. So that's used in nuclear weapons, and it's also used to generate nuclear power. And nuclear power and these type of reactions are a big part of the way New Jersey currently gets their electricity. Okay. Nuclear fusion we rely on heavily because it's what the sun does. It brings things together. And as these things come together, they also release a lot of energy. That's what the sun does, and it keeps on doing for us perpetually. So it's happening all the time. We have not been able to recreate that here, and that's something that people are trying to do, trying to find out fusion to create energy on Earth. That would be very interesting, but it seems to be a little bit elusive. Okay, so matter can't create it or destroy it, so it's going to break down from one form to another, and that's the question here. What are we doing when we do that? What do we end up with? What are our products? And is it matter that is lower quality than what we started with? And we can tie that into non-renewable resources. We can tie that into so many things. Look for the connections at all times. Okay, so these equations, when we change it from one form to another, are put together, these reactions, I should say, are put together in balanced chemical equations, which you've seen from chemistry also. The subscript means that here the oxygen has 2, the 6 in front of it means 6 multiplied by everything. The carbon here on the far left-hand side has no number, that's 1. So for this CO2, we have 6 carbon and we have 12 oxygen. So that's the idea of the balanced equation, probably a review from chemistry for you. As far as that goes, do you know what that is? CO2, that's a pretty common one, right? Carbon dioxide. Okay, so carbon dioxide, if it reacts with 6 H2O, 6 waters, then here on the other side is the product. So if I added up all the carbon and all the hydrogen and the oxygen, it has to be balanced with what's on the other side. And that's the conservation of matter. Okay, so carbon dioxide plus water What is this one over here? This was on the common molecules that you have to know. Do you recognize this already? This is glucose, and that's a sugar that is really important because it provides so much energy on this planet anyway. Really, that's where it all starts. And also gives off oxygen. So this is a pretty important reaction, right? Takes in carbon dioxide. We can't breathe that, right? And a little bit of water, kind of add in some light there, and for it you get glucose and oxygen, and we all like oxygen. Do you know what this is, this equation here? No, you should get to know this one if you don't already, and if you do already, you knew it was photosynthesis. Pretty good one. All right, well, photosynthesis, because all of our energy does come back from that sunlight and this reaction here, because that gives us all the plants, and every bit of energy that we have can be tracked down to the sun and to plants. So this is the reverse of it over here. This is where we take glucose, we take in some oxygen, and we give off CO2 and water and some energy. And that energy allows us to do everything that we need to do. And this is respiration, and that's what we do, respiration. Okay, so energy is the ability to do work, and energy can be changed from one form to another. So that glucose energy that's wrapped up in that sugar, it doesn't stay as glucose. It turns into physical work that we're doing, maybe kinetic energy, the energy of motion, and then maybe some heat is given off, and that would be heat energy. So energy is going to be changed from one form to another, and energy is the ability to do work. Okay, so here I'm talking about kinetic energy. Kinetic energy is the energy of motion. Something in motion can do some work. If you have something moving and it hits something else, it can certainly do some work on it. And there you go. So that's kinetic energy. And we also have heat. And heat is a form of energy as well. And that is transferred in by radiation. And we could also talk about light being transferred that way as well. And we're going to have a slide that shows that in a little bit. Potential energy is where energy has been stored up. The glucose is potential energy until you start doing some work, when you get up and get going. And gasoline is stored energy until it does the work of the automobile. And yes, this potential energy can be switched into kinetic. Even gravitational, if some of you have taken physics already, you know you've talked about that. You're stored up with gravitational energy, and then that can turn into the movement of kinetic energy. And that has a tie into environmental science. We need water. Water always flows downhill. From the sky, we need gravity, and then we also need gravity to bring it down from mountains to lower places, and there we go. All right, so here's the idea of the electromagnetic radiation, and this is the stuff here that's coming from the sun. So this is what we can see from the sun, but we get all of these other forms of energy from the sun, and we'll talk about that. Ultraviolet radiation, that has a concern for our class, and infrared is the heat, and the heat certainly affects our planet, that's for sure. Okay, so here's a nice little picture to show you what's going on. And really what this one here is talking about is that every step along the way you're going to waste some of that heat. And the rule of thumb here is that 90% of it is wasted as you go from one step to another. So the light going to the ground has a certain amount of energy. 90% of that just goes into heat, but 10% of it goes into moving up the food chain here, or watching how the work is being changed from one form to another. This is talking about energy transformations. So now it goes into making the apples, and then we lose some, and then the rest of that becomes food, and that becomes the person moving, but they're going to generate heat as well, work up a sweat there as you're digging a hole, and so we lose a bit on each step. That's what that's showing. So just like we had for matter, we also have for energy, high quality and low quality energy. And the idea of that is that you're going to go through these energy transformations, but each time the energy is a little bit a lower quality energy. When you have the food that's wrapped up in the apple in the last diagram, that's energy that's higher quality, and when using that apple, you know it's higher quality because you're going to have all that waste. So you're left with something that is a little bit lower quality, and the waste ties into that. Okay, so we have to talk a little bit about physics here. Like I said, there's all these different things tied in, and this is part of the building blocks. And thermodynamics is talking about heat and energy, and the idea is whatever you put in is what you get out. But also, that's the first law, is you get exactly how much you put out, but it is of less quality every time you go through a step. And that's important too, the second law of thermodynamics. And that ties into energy efficiencies. And efficiency really means how much are you losing. So if you can cut down on the waste, you're really probably saving yourself some energy, definitely. And we keep getting more and more efficient in our energy processes. And also, probably from an economic standpoint, you will be saving money because you'll be losing less energy, and energy does come at a cost, right? So that's the idea there. Okay. Excuse me. Okay, so what are systems and how do they respond to change? This is where we'll finish up this chapter 2 here. And the idea are systems, and this is again a way of talking about the connections. Systems are things that go from one form to another, or they flow from one place to another. It's really showing about the connections here. So you've got something connected to another thing, and then there's an outcome, and the more we know about these connections, the more we know about what's going on. So an example is our economy is a system, right? We bring in these resources, energy and matter and what we know here. They go into the economy, and then there are outputs as well. We get the things that we like, the goods and services, but we also have waste and pollution, and then there's heat that's going off. So these are some of the connections here, and really impossible, in my mind anyway, to separate economic and environmental and economic issues, at least in this day and age. Well, when we're talking about these connections, another way of talking about these connections are what they call feedback loops. So if you do something, how does it affect the other thing? And when it does it cause somewhat of a chain reaction here? That would be a positive feedback loop where one thing builds on another, or is it something that corrects itself? And that's a negative feedback loop. These terms are used widely in the course, but they're a little confusing because positive seems like a good thing. But you could have a positive feedback loop with negative consequences. And we'll talk about a lot of those as the class goes on. So here's a positive feedback loop. You cut down on some of the plants from step 1 to step 2. Well, that means you are going to degrade the soil. And when you do, there's less nutrients in there. And when there's less nutrients, less plants can grow. And if less plants can grow, there's more degradation, which means to less plants being able. So this is a positive feedback loop. It just keeps going in one direction. And you could probably argue that this is a positive feedback loop with negative consequences. A negative feedback loop is like a thermometer. The temperature gets too high, the temperature gets cooled off. The temperature gets too low, the heat goes back up again here, right? So that's the idea of a negative feedback loop. It'll kick you back in the other direction. Population in natural setups works like that, right? If the population of the prey species gets too high, there's not enough prey, so it's going to go back down again. If it goes back down too far, there's more prey than there is predators. The predators will go back up. That would be a negative feedback loop. Okay, that's it for Chapter 2. I hope you found this informative, and if you have any questions, of course, bring them to class, and I look forward to seeing you there. Thanks for watching.